Okay, so let's turn to slide 15, example 4.08. A 1,600 pound-inch couple is applied to a rectangular wooden beam in a plane forming an angle of 30 degrees with the vertical. Determine the maximum stress in the beam, the angle that the neutral axis formed with the horizontal plane. Okay, so we have a unsymmetric bending. So how do we find that stress caused by this moment? We need to break it up into two components on the y-axis and the z-axis. So this is my, you're going around the y-axis here. mz, you're going around the z-axis. So break it up into two components. The stress caused by moment m equals to the stress caused by a moment mz plus the moment caused by my. Why do we know that? It's just vectors, right? Here, tail tip method, vector mz plus vector my will equal that moment there. Okay. So our goal is to find out when this stress is maximum stress. This equation is at maximum. Okay. Let's turn to, okay, before we go to the next slide, some of you might be wondering, why is it stress X? Let's look at a member that's going along the x-axis. The longitudinal axis is along the x-axis. You have a moment about the z-axis. You see here that the top is in compression, top half is in compression, the bottom half is in tension. This moment's going to cause pressing in along the x-axis and stretching out along the x-axis. So that's why it's stress X. Because the stress is moving along the x-axis. So when the member is along the x-axis, then you're going to be calculating for stress X. Okay, so Becca asked to review again, how do you know when it's in compression or tension? So this is the member along the x-axis. This is the member in pure bending. So wherever the arrow points, that's where it's in compression. And here is in tension. So it's pointing to the top. So here it's in compression, here it's in tension. This is what the member is going to look like in bending. This top is going to be the most compressed, the most shortened, and the bottom here is going to be the most stretched out. Okay, so where the moment points to, that's where there's going to be compression. Okay, so let's turn to slide 16. Okay. When you break up the moments, make sure again that the arrows point in the same direction. So here it's going from left to right. Well, make sure the moment is spinning in the same direction. So here it's spinning left to right. So you're going to break it up the same direction, left to right, and here left to right. For example, if the moment was this way from right to left, then when you break it up to the two components, it'll also go from right to left and spin the other direction. So right to left. Okay, so make sure when you split it to two components, the moment spins in the same direction. Okay, So slide 16, moment about the z-axis is cosine theta. So this, the moment is going along this 30 degrees plane, and the moment vector is perpendicular to that plane. So this, it's a 30 degrees from the vertical. So this angle will be 60 degrees because these two added together is 90 degrees, which means this angle is 30 degrees because these two angles added together is 90 degrees. Okay, so theta is 30 right here. So mz is m cosine theta, my is opposite here, this opposite angle, so that's m sine theta. So my is m sine 30 degrees. Okay, so we get mz equals 1,386 pound-inch, my equals to 800 pound-inch. Okay, so mz equals m cosine 30 degrees, my is m sine 30 degrees. Okay, again, we're trying to find values for each of these terms. Okay, so we found mz, my. Okay, so let's find iz and iy. This is the cross section that we're looking at. By the way, the member is going along the x-axis. Okay. Okay. Just know that the member is going along the x-axis. Okay. So this is the cross section. This length is 1.5. Top and bottom is 1.5, and then the left and right is 3.5. About the z-axis, moment of inertia equals both of them 1/12 bh cubed. When it's about the z-axis, the bottom and top are b, the left and right are h. Okay, so that's 1/12. B is 1.5 times 3.5 cubed. When it's about the y-axis, now b, it's about the y-axis, so b is this. So b is now this length. Okay, so that's b is 3.5 and h is here, 1.5. So that's 1/12, 3.5 times 1.5 cubed. Okay, so iz is 5.359 inch to the fourth. Iy is 0.9844 inch to the fourth. Okay, so we found iz, iy. Now we need to find y and z. Okay? The y term, you're always going from the centroid to either the topmost, bottommost, or the rightmost and leftmost. So it's y, a y term, so it's going to be 3.5 divided by 2. So the y term is 1.75. So that's half of this vertical length here. The z term is along the z-axis, so that's half of 1.5. So it's from the centroid to the right or the left. Okay, you always go from the centroid. So z is 1/2 of 1.5, so that's 0.75. And this is in inches. Okay. So you have the y term and the z term. Okay, so you get that this first term here is 452.6 psi, and the second term here is 609.5 psi. Okay. Now we're trying to find when stress is at maximum. Okay, so let's turn to slide 17. That is a 3D picture of what the stress looks like for that cross section. Okay, so this moment about the y-axis, the right is going to be in compression. Rightmost is going to be the most compressed. The leftmost is going to be in the most tension, the most stretched out. This moment about the z-axis, the topmost is going to be the most compressed, and this will be the most stretched in tension. Okay? So we know that this point is going to be in the most tension, and this point is going to be the most compressed. So how do we find these two numbers? Okay, so we know that for my, here it's negative 609.5 psi. On the left, it's going to be positive 609.5 psi. For the moment about the z-axis, it's going to cause a stress, and these are stress. Okay, it's going to cause a stress on the top of 452.6 psi. And this stress, it's going to cause a stress on the bottom half. Well, on the bottommost is going to be, this is negative, and this is positive 452.6 psi. Okay? So this point right here is just going to be negative 609.5 psi minus 452.6 psi. So this point, it's going to be negative 609.5 psi minus negative 452.6 psi, which equals to negative 1062 psi. Here, it's going to be the stress caused by a moment about y-axis plus the stress caused by moment about the z-axis. So it's positive 609.5 psi. That's the stress caused by this moment plus the stress caused by this moment plus 452.6 psi. So that's going to equal to positive 1062 psi. Okay, so this is maximum tension here and maximum compression here. Okay. Slide 18. Determine the angle of the neutral axis. So you just plug into the equation. Tan phi equals to I z over I y tan theta. Okay. And this is when y is vertical and Z is this horizontal axis. Okay. Okay. So we just plug in the numbers. IZ is 5.359 and IY is 0.9844. And tan theta. Theta is from the horizontal axis to the moment vector. Okay? So we already said how to get to this 30 degrees right here. So this is theta. This angle from horizontal to the moment vector. So IZ over IY tan 30 degrees. That's going to give you 72.4 degrees. Okay, and we are on slide 18. So this is visually the neutral axis. 70, this angle is 72.4 degrees. Okay. So this is when there's this is where there's not going to be deformation right here in that cross section. Okay. Okay, so that's the end of that sample problem. Now let's move on to our last subject. General eccentric loading. So we're going to go 3D now, and it might take you some time to understand and visualize. So you might need to take some time on your own just to look at the drawings and make sure you understand it. Since we're moving on to 3D, it's more complicated. Okay. So before we only had two terms. What we talked about, eccentric loading. So we had the centric load plus the stress from the moment. But now we're doing 3D. So this eccentric loading, an equivalent now is going to be the centric load plus two moments. Okay, you see this load is going to cause a moment about the y-axis. Okay, and the moment arm is A. It's also going to cause a moment around the z-axis, and the moment arm for this load is B. Make sure you understand the direction of these moments. This is going to go from left to right here. Okay, it's going to do a moment like left to right here around the Y. Here around the Z, it's going to go upwards. Okay, with B as the moment arm, so it's going to go upwards like this. So make sure you understand the direction of these moments right here. Okay, and again, be careful of the signs. These signs all changed based on whether you're in compression or tension. So here, this P is going outward, so that's positive. And depending on where on the cross section you're looking at, yeah, you'll be negative or positive. So negative is compression, positive is tension. And again, stress X equals to 0. When you make the stress equal to 0, it'll give you the neutral axis. We're saying stress X because this member is going along the x-axis. If, for example, you have a member going along the y-axis, then you'll be looking for a stress y, which we're going to do a problem that we're looking at stress y because the loads and the moments are causing deformation along the y-axis. Okay, so this will be, we're looking for stress y. When it's along the x-axis, we're looking for stress x. Okay, so let's turn to our last sample problems. Example 4.09. A vertical 4.80 kilonewton load is applied as shown on a wooden post of a rectangular cross section, 80 by 120 millimeters. Determine the stress at A, B, C, D, and locate the neutral axis of the cross section. Okay, so notice that this wooden post is going up and down. It's a vertical one. So we're going to be looking for our stress y. Look at your slide 20. You're going to look for the cross section here, A, B, C, D. I'm going to look at a cross section in the post. And notice that it's at the four corners, so you need to look at stress maximums. Okay, stress max and mins. Okay. Determine the stress. So again, we're gonna use this general eccentric loading equation right here. Okay. Let us find mx and mz. This load is going to cause a moment about the x-axis, and A is the moment arm. The moment arm is going to be 80 divided by 2. So moment about the x-axis is 4.80 times 0.04 meters equals 192 Newton meters. Okay, so again, what are we doing? This is an eccentric load, so we're going to find an equivalent, which is eccentric load plus 2 moments, x and mz. Okay, so this eccentric load is equivalent to a centric load at the centroid plus 2 moments. We can't really find eccentric load directly on its own, so we know how to find a centric load and a stress from 2 moments. So we can add them together to find this the stress that this load is causing at this cross section. Okay, so the goal of what we're doing is to find the stress that this eccentric load is causing at section A, B, C, D. That is our goal. The stress that this eccentric load is causing on section A, B, C, D. Okay, so the centric load is the same, so so look on slide 20, you have a load and 2 moments. and you're moving this load right here, you're gonna move it to a centroidal principal axis. So this is going through the centroid right here. Okay, so this load is 4.80 kilonewtons. This moment mx is the load times the moment arm A, which is 192. The moment arm is 0.04, so it equals to 192 Newton meters. All right, so this one's a little trickier, but the moment arm is this B, and this load is left of the z-axis. So try to take some time on your own looking at this drawing, but it's from, the moment arm is 120 divided by 2, so there's 60 millimeters. The 60 millimeters minus 35 millimeters will give you this B. So this B is the moment arm, and you're gonna go around the z-axis, okay? You see that? It's right of the z-axis, and it's gonna have this motion right here, okay? You're gonna have this moment like this around the z-axis. So mz is equal to 4.80 times 60, half of 120, 60 millimeters, so that's 0.06 meters minus 35, gives you this B here. So that will give you 120 Newton meters. So, and make sure you have the direction right. It's going like this. It's left, going left. Okay. So we have mx and we have mz. Now let's turn to slide 21. Okay. Okay. So again, the equation that we're looking at is stress Y equals to centric load plus or minus m mxz over iz plus or minus mz x over, oops, this is x, this is z. Okay. So if you're looking at stress y, then it's going to be the other two variables, mx and mz. And this number, this variable is going to be that third variable. So there's x, there's y, so this is a z variable. Here mz, it's zy, so this is an x variable. Another way to look at it is that this moment is going about the x-axis. It's acting in the plane that's coming out. And this is a 80 millimeters, so it's acting on the plane that's coming out of the board. Here, mz, so that's a z component, that's 80 millimeters. this MZ is acting in a plane going left and right. It's this plane, left and right. So it's this X plane. You're concerned with this X number right here. But for problems, just practically, it's just you have stress Y and you have mx, so it's just the third variable, z. And I is the x, same as the moment. So here it's stress y, and then moment is around the z-axis, so it's just the third variable. Okay, it's just going to be the third variable, x. Okay, so for us, z is going to be half. It's always from the centroid to here it's 40, half of 80. Here it's the x variable, so it's from the centroid to the rightmost or the leftmost, so that's 60. So here z is going to be 40. Here x is going to be half of 120, so it's 60. Okay. Okay, so slide 21, you find Ix, Iz. I'm not going to go over that because I kind of went over it in the last problem. It's just 112 BH cubed. Make sure you know which one's B, which one's H. A is just the area here. So that A is just 80 millimeters times 120 millimeters. Okay. Again, we're trying to find all the values for these. So A is 80 times 80 millimeters times 120 millimeters equals to 9.6 times 10 to the negative 3 meters squared. P is given 4.80 kilonewtons. Ix and Iz, it's 112 BH cubed. So that's 5.12 times 10 to the negative 4 meter to the fourth. 11.52 times 10 to the negative 6 meter fourth. Z is 40 millimeters, right? It's coming out of the plane. Mx is this z distance along the z-axis, so it's 40 millimeters. X is along the x-axis, so it's from the centroid to the left or the rightmost, so it's 60. Millimeters. Make sure you convert everything to meters. Okay, let's turn to slide number 22. And we have mx. Mx is 192 Newton meter. Mz is 120 Newton meter. See, we found it here, remember? Okay, so we have all the numbers. We have all the numbers that we need. So the centric load, the stress from the centric load equals to 0.5 megapascals. The stress from moment about the x-axis that is 1.5 megapascals. The stress by moment about z-axis is 0.625 megapascals. Okay. But again, these are all plus minus depending on where on the cross section you're looking at. Only this one for sure is a negative because see here, it's a compressive force here, right? It's a compressive force, so it's a negative for all, for A, B, C, D, it's all compressive. So only this one doesn't change. Okay, so let's turn to slide, okay, so here we have a compressive centric load, stress from the centric load plus or minus stress from the moment about x-axis plus or minus stress from the moment about the z-axis. So we have values for these. We just have to determine if it's a positive or negative. So A, B, C, D. So we're looking at cross-section here, A, B, C, D. We have this moment about the x-axis. Where the arrow is pointing to tells us if it's in compression or tension. So here, the bottommost is going to be in compression. The topmost is going to be in tension. So C and D are going to be positive for stress 1, which is the moment about the x-axis, okay? So D and C are positive for stress 1, and A and B are negative for stress 1. How about for the moment about the z-axis? The leftmost here is going to be in compression. That's where the arrow is pointing to, the left. And then this part is going to be in tension. So D and A are going to be negative. D and A are going to be in compression, and C and B are going to be in tension. Okay? So turn to slide 23. Does that make sense? So let's see. So for stress A, that's going to be negative stress from centric load, negative 0.5 megapascals. That's from the centric load. And then stress A, it's negative, stress 1 on A is negative 1.5. Okay? And then here at point A from stress 2, that's also negative. Negative 0.625 megapascals. So stress at A is negative 2.625 megapascals. Now let's look at stress B. We have that centric load, which is negative 0.5, compressive centric load. So the stress from that centric load is negative 0.5. B, negative stress 1. So negative 1.5. Here, B is positive, so positive 0.625 from stress 2. It's a positive, so that's equal to negative 1.375 megapascals. Stress of C, stress of centric load is negative 0.5. C, so that's positive stress 1, so positive 1.5. This is also positive, so positive 0.625 equals to positive 1.625 megapascals. Let's look at stress at point D. We have that compressive centric load. Now let's look at D. It's a positive stress from moment about the x-axis. So positive positive 1.5. Okay, D is negative from stress 2. So negative 0.625. So that's going to equal to 0.375 megapascals. Okay, so that's where you get how you find the stress at each of the points A, B, C, D from an eccentric load. Okay, we're almost done. So now we want to find the neutral axis. The neutral axis is when there is no stress. How do we find that? Okay, we have the stress at each of the points A, B, C, D. So the question is, locate the neutral axis of the cross section. So we want to know where stress is 0. Okay, turn to slide 24. That's a 3D picture of the stress distribution for that cross section. Okay, so at A it's negative 6.25 megapascals, B it's negative 1.375, C it's positive 1.625, D it's positive 0.375 megapascals. When is stress 0, you're going to see when it crosses over from positive to negative or negative to positive. There's a change in sign. So there's a change in sign between C and B, and there's a change of sign between D and A. There's no change of sign here, DC or AB, so it's not going to cross to 0. It's going to cross 0 between C and B and D and A. How do you find point H and G? You do what we've done before, just similar triangles here, and use ratios to find the point where this linear line crosses the horizontal line here. Okay, so slide 24, it tells you the ratios that you can use, and then you find that BG is 36.7 millimeters. And HA is 70.0 millimeters. Okay, so we found the point where this is the neutral axis for this ABCD cross section where stress equals to 0. Okay, that was really long, but thanks for getting through it. And homework, we'll 4.13 and 4.14 homework due next Tuesday, and please write comments in the discussion tab for today's lecture. I made responses to your comments from Tuesday. Okay, hope you have a good weekend. God bless. Take care. Praying for you guys. Bye.